新松田です。
And then kind of the Nest for the level aspect myself in 2011. Many more people like Yuki who would find this kind of stuff quite a bit, which says that under the conditions I've written down on the right-hand side, this squared period is given by an L function. So this is some degree 8 Euler product, which it would do us no service to define, divided by an analytic conductor. And I'll put in this analytic conductor exponent a little o of 1. Well, the meaning of little o of 1 is something that tends to 0 for psi fixed, and let's say the parameters of phi tending to infinity. The L function is known in this case to be non-negative value. No, we should. So I mean, in fact, so okay, I guess this formula proves it, but yeah. And just for the sake of expediency, I'll introduce the definition. I'll call this right-hand side L over c to the quarter plus little o of 1. Okay. So this is all still like a very standard direction. Here and then reduces to the following estimate that I'll call star, which says that L over c to the quarter is bounded by, well, the same c raised to the negative delta times, let's allow some polynomial dependence on the conductor of psi, maybe to the 1,000 or something like that. So this is for some delta greater than 0 and maybe a greater than 1 million. And so, I mean, those of you who know this is a bit of a subconvexity problem, so we're going to address this by proving a subconvex bound in this case. And it's worth also noting that in this case, so this number I've defined to be c up here happens to be roughly of size p to the 4th. And these are fixed values of psi. So saving a power of c is the same as saving a power of b. I guess I'll leave the theorem stated in the middle for now. Okay, now let's do kind of a very tautological further reduction. So I call this estimate asterisk. So clearly theorem Mn follows from asterisk. Let's divide asterisk into two cases. Let's call one case case A and one case case B, where A is the case of asterisk in which the kind of fixed function of psi is an Eisenstein series. Let's call assertion B the case where psi is indivisible. So those are, of course, the two possibilities, so if we treat both of those, then we have the theorem. So then the structure of the proof has a very kind of interesting form. So on the one hand, I'll put it in the same word. So this will also explain the division of the credited theorem. So theorem M I'll state as the assertion that A holds. And then theorem N, with the credits and the names kind of in the obvious parallel sense up there. So you'd expect it to say that B holds. But I mean, to be kind of a bit more honest, what it actually shows is that A implies B. And then the two of them together, of course, imply what I call theorem NN. So for emphasis, this is Munchi, and this is myself. So I want to spend the rest of the talk kind of explaining the proof of what I call theorem N here, like why in the world there should be any implication between two results of this shape. But I don't think there's any pre-existing intuition or kind of model result in which to base an implication like this. I mean, for most purposes, the contributions of these two parts of the spectrum don't really see each other. But for here, I mean, I should say, I mean, the preprint is still being finalized, so we should, well, I mean, it is being finalized. We talked about it, Munchi and I, quite a bit while he was here. This preprint is at least available and submitted, so that's what I'll talk about for the remainder of the lecture. And maybe it's worth noting that in this theorem, what I call theorem A, the case where psi is Eisenstein, there's a factorization of the L function into Euler factors of degree most 3. And so that's the actual problem he addresses. And it seems pretty clear that the technique does not apply to the higher degree L function that comes up in part B. That's an interesting question. So at present, my result seems to require square free level without further work. So it requires something really non-trivial to do any other aspect. Maybe ask me at the end of the talk again. I'll say a bit more, but Munchi's result is not quite clear to me. I can imagine square free level would be no issue, but there's a very, very bizarre restriction in the method at the moment to essentially grand level. So let's talk about the proof of theorem M. So let's remember what we started with. We wanted to bound L over c to the quarter plus little o of 1. So we can take a step back for a second and remember where this came from. This came from basically the air product of phi against psi phi. That's a suppose here that phi is LT normalized now. So it's all squared. So the way I got into this problem came from some work I've been doing over the past 7 or so years, where I've been studying expressions that are nonlinear in phi by using something called the Shimizu theta lift, which basically expresses phi of z1 times phi of z2 as an integral that I don't have time to explain in detail, but it'll be an integral of, say, phi of w against some complicated theta function depending upon all three variables. And it turns out that if one plugs in a sufficiently precise form of this identity into this inner product, one gets an expression of the following shape, where I'll define everything on the next board. So I'll call it b theta sharp h sharp squared. And so the first step in the proof is we're going to study this ratio of L functions, or equivalently this period, by means of this particular integral representation. Now, I'll mention, in fact, so actually in the article, there's a lemma of Yang and Chu that he proved on some other results on static current correlates together with some local calculations that I worked out that kind of give this error directly. Anyway, I mean, his proof actually goes through the same set of implications. So the first step is to kind of linearize the problem with respect to phi using the Shimizu lift, and then zoom in on that lower item. No, I haven't told you what anything is in that inner product, and that'll come in a second. So imagine that I wrote where ... on the bottom. Yeah, phi is LT1, as in the right. So phi, okay, yeah, so let me put some thoughts here. And say this, I mean, this will be off by something like the difference between the arithmetic and analytic normalizations of phi. So there'll be factors like L of hat v1 floating around in there. Okay. So we reduced to showing the following, that this inner product phi, theta sharp, h sharp is bounded by phi to the negative delta. Now here, let me spell out everything. So theta will just be the usual Jacobi theta with a y before the front. Theta sharp, I just need a quick way to write theta of pz. Some notation. So I'm going to define h before h sharp. H will be something like the inverse Mas-Shintani, or inverse Shimura, or Mas-Shintani-Walls-Berger lift of psi. So it'll be written in the following form. This is something like, I don't know the best way to say it, but something like the inverse Shimura lift of psi. And then finally I can define h sharp. So h sharp is what you get by putting a p in the argument there. Now we're on the next board. So h sharp is a half integral waveform on gamma naught of 4d. Because we're emphasizing that all of these h's depend upon psi. That's where the enters into the discussion. And there's a useful fact, which is that it turns out that h sharp has the same LT norm as h. It's not entirely obvious, but plays a useful role. So in this inner product I've written down here, all three of the forms are effectively unit vectors. And the fact that you can actually position yourself, you can find an integral representation where all three of them are unit vectors, and they satisfy some other nice conditions, like one of them is unramified. This is kind of specific to this Webber level aspect, and represents one of the obstructions to kind of generalizing this method a bit further. Okay, so we arrived at this problem of bounding this inner product by a small power of p to the negative delta. So now there's a technique called the amplification method. So, due to various people, Vanya Sarnak, Ukraine Leonard Donich, Venkatesh, Michelle Venkatesh, in the 90s and early 2000s. So what I call star will follow from isolate third star, where triple star will be the assertion that if we take phi multiplied by theta sharp, and then we take the LT norm, then we can produce an asymptotic formula for this LT norm. Plus some very small error. And I'll say informally with a bit of room. So in the last few minutes of my talk, I'll explain how to actually prove triple star, which is really the meat of the whole argument. But before I do that, I want to say just a couple more words to kind of give you an indication of why it's plausible that triple star should be sufficient. So what we really need is, so we're going to use half integral heck operators. So for small l, that are squares, maybe l is of size p to the alpha, where alpha is small and positive. So what we really want is to show that if we apply a heck operator to p theta sharp, then we get 1 over the degree of the heck operator, which is something like L, times the corresponding inner products on the right-hand side. Plus an error that is like small in p, and maybe polynomial in L. delta LWA. So the meaning of a bit of room to spare is that when we write down the proof of triple star, it'll kind of be very obvious with every step that the proof more generally extends to give whatever this number here. And so the amplification method is all about taking a statement like this and using it to buy a little bit in the main term. So the idea is that if star fails, then Cauchy-Schwarz identity, B, theta sharp, H sharp, so this being bounded by, say, B theta sharp squared. So this is nearly sharp. So morally speaking, B theta sharp is kind of nearly a multiple of H sharp. Which can be seen to contradict whatever in here. Say triple star subscript L. Contradiction here is because so typically TL H sharp is something like, well, lambda B of H sharp through L. This is typically about 1 times H sharp. And you can check that if you apply TL to B and to consider product and do the same thing with H sharp. This side here is bounded by L to the 3/4. This side here is bounded by say L to the quarter plus 7/64. Which is in particular bounded by L to the 3/4 minus beta. So this is bounded by L to the 3/2 minus beta, which I can write as 1/2 minus beta times the degree of TL, which is contrary to the asymptotic relation that I've written down here. So the remaining question that I'll address in the last minutes of the talk is how do we actually establish triple star? So we use the spectral theorem on ultimate H mod SL2Z. Right, so I'll make 2 remarks about this.